Hello everyone, this is Aryan and I welcome you to watch the development of my latest creation, the quadruped. In this video, I will demonstrate how to use a control rig and I will show you how you can use simple math operations to animate this character. The source code is available in my GitHub account and you can also find the character source files inside my Patreon. You can also watch the time-lapse of modeling and rigging of this character, which is the previous part of this video. I left you the links in the description. Now, if you are ready, let's start part 2. Okay, if you have watched the part 1, you have seen that we used vertex coloring instead of texturing. In order to give the character its proper look, let's create a new material and call it mRobo, which is by convention the standard style of naming Unreal assets. Now we can start by adding the vertex color node to the material graph. And let's connect it to the base color and emission to reduce the amount of shadows casting onto our character. You can also multiply the emission by half and give it a better look. Now let's take a look at our character. I think the contrast of vertex color is not good enough to be used inside Unreal Engine. Let's bring it to the power of 3 or 4. By doing this, it will increase the color contrast. Now let's create a control rig. Control rigs are very similar to blueprints, but they also provide tools to rig your character, introducing IK solvers and many functions to manipulate the bone positions. But before that, you have to import all the bones into your control rig. You can easily do that by clicking the Import Hierarchy within the Rig tab. So let's settle by creating a control point for one of the legs. For better readability, let's name it IK front left. You can also change its shape to something like a circle and scale it up a little bit. Then you can move it to its correct position. Then, by right-clicking on the control point from hierarchy, you can set its offset position to match the closest bone. As you can see, the initial and current position are zeroed out and the offset is set to its correct position. So every time you click on the compile button, the coordinate will stay the same. Now you can add a solver node, for example, the fabric solver. The fabric solver takes an effector which we are going to assign it to the IK we just made. Then for the bone data, we are going to create 4 slots. One by one, we are going to assign them to their correct bone name. As you can see, we can simply change the IK position and then the solver immediately corrects the transform of each bone to reach the destination. Now for the other legs, we are going to duplicate the IK. And then we repeat the process for each and every leg. I think I forgot to bake the offset position, so it did reset to its original position, which is 0. You can also make sure their offset rotations are cleared out. Next step is to duplicate the fabric solver and repeat the process for other 3 legs. Now let's fix the bone names for each solver. Congrats! Now you have 4 working legs. Now it's time to rig the root bone. In order to do that, we are going to set its position before solving any legs. Now let's create an IK for the root bone. We can also give it a better look, like a solid circle. Also make sure you clear the rotation, cause we don't need that. Now it's time to mirror its position to the root bone. Perfect, now we can move the character's butt. But there's another problem. When I move the leg, I expect the root bone also follow along. In order to do that, let's separate the root transform coordinates. Then we can create a function to calculate the correct Z position. And of course, we don't need the execute pins. Let's remove them and make this function pure functional. Then we can add a pin to the return node and let's call it Z. Now, all we have to do is to calculate the maximum Z position of all the IKs and return it from the function. Now we can use this function to set the Z position of the root bone. Now it's time to create an animation blueprint from our skeleton. In order to use the control rig, we need an ABP. ABP will act as a bridge between the rig and the character itself, which we did not create it yet. Now let's add the input pose node and connect it to the control rig. In the control rig properties, let's set the rig class. We also need a new data type, so we can pipe the IK transform into the control rig. For this purpose, we can use Unreal Engine's structure asset and let's call it sRoboLeg. Since we are going to use this struct in an array, we are going to need 2 variables, one for the control name and one for its location. The control name must be as type of name and location must be as type of vector. Now we can create a new variable inside the control rig. Let's call it legs and set it type to our newly created type RoboLeg. And we make sure it's an array. Now we can iterate over its items and set the IK transforms. By dragging one of the IKs into the graph, we can simply assign the control name and translation from the leg structure. Now from the Blueprint tab, let's make the legs variable instance editable. Next, in the ABP, we can enable the legs variable inside the control leg by clicking its Use Pin property. Now that we have the ABP, let's create the character blueprint. We pick the character as a parent class because we know that our character is going to move. Okay, so now let's pick the mesh component and assign the ABP to the character. Also, don't forget to save your asset regularly, that's a caution. We should also create the legs variable over here. After compiling, you can edit the variable and initialize it with default leg configuration. Let's add element for all 4 legs and initialize them with the correct IK names. Now let's head back to our ABP and read this value from our character blueprint. In order to that, we are going to the event graph and we'll override the init function. Then in the init function, we are going to cast the pawn owner to our newly created character type and then store it in a new variable called character. Now we can go back to the anim graph and use this variable to set the control rig's leg variable. After saving everything, let's add our character into the map. As you can see, the legs are now targeted to 0 coordinates of the character space itself. In order to have procedurally animated legs, we need them to target toward coordinate system. I also made a mistake by using begin play event instead of initialize animation. That's why you are seeing this error. In order to fix that, let's go to the ABP and override the correct event, which is the initialize animation. As you can see, the error is gone. Now let's fix the coordinate system. Let's go to the control rig and add a node called from word to correct the location retrieved from the character. Everything looked good. Now let's apply some raycast to make it more interesting. Okay, let's resize our collider and move the mesh component to fit into the capsule. As you can see, it's like nothing happened, but actually it did happen because in the control rig we are setting the root position to maximum Z value of all the legs. We can simply ignore this for a moment and move on. Now let's create a new variable for the root location. And let's enable rendering of characters capsule in the viewport. Now let's set the root IK position. Introduce a new variable of type vector. rearrange the connections. Okay, now let's open the ABP and set this variable. Now let's set the center value to actor's location. But it would be better if you raycast from the actor's location and find its location on the ground. Actually, let's make a macro to simplify the whole process. Let's add a sphere trace node. Also add a branch node to check whether it's hitting any obstacle or not. We should also define the inputs and outputs of the macro. In the output pins, we also want to expose two different flow conditions, one for obstacle being hit and one for not being hit at all. We also need to expose the location of impact to the obstacle. Also enable some options for debugging. For the inputs, we are going to take the location of the ray, which it starts, and the endpoint. And of course, since this is a sphere cast, we need to define the sphere's radius. Okay, so now let's use this function inside our event graph. To use this macro, we also need another function to calculate the ray start and ray end based on the actor's location. So let's create a function. The function will get the minimum and maximum z from input and will calculate the start and end vectors. Now we can connect the x and y components to the output. And to calculate z, we need to only offset the input z value based on upper and lower levels. Okay, so now let's use this function to finalize our raycast. Let's see how it worked. Okay, I think I need to swap the lower and upper levels. I think that our character is finally grounded. But what should happen when the raycast not hitting the ground? We can set the center to actor's location. We can also use the mesh component relative location, which we did set earlier as an offset to actor's location in the word. Okay, now we can set the x and y value to the center, and we can set the center z to some of the actor's location z and offset from the ground, which we assign to the mesh component. it's not working right now, but we'll get there. Okay, now that we have set the root IK, it's time to initialize the legs for our character. Our character will move, but how it will keep itself balanced? Let's assume when the bot is moving, there are at least 2 legs planted to the ground, and other legs will be free to move. And when the movement distance becomes larger than some value, the bot must swap its legs and continue its movement, like in a cycle. But first, we need to initialize the leg positions. To do that, we need another variable in the RoboLeg structure to store the initial state of the legs. And another variable to check if it is planted to the ground, so otherwise we could move that leg. And we also need to define the toe names for each leg to initialize them from their actual position. Of course, we have control names, but they are not accessible through our blueprint. Now, let's define these variables inside our blueprint. Let's set the legs in a zigzag pattern and properly define those toe names. Now it's time to set the leg initial position. Let's use a for loop node to iterate our legs. Break the array pin so we can use the toe names we just created. Then use a setStruct property node to assign the offset to each leg. Then in between, we are going to get the toe position from the mesh component. Then we use a Raycast node to determine where it landed on the ground. Now let's change the upper and lower levels for the Raycast. Let's set the initial location of the leg and calculate the initial offset by subtracting the impact point with actor's location in the world. This will give us the relative offset to the character itself. We also need another variable to determine whether the legs are initialized or not. Let's create another variable called ready as type boolean. So when the loop is complete, we are going to set this variable to true. Back to control rig, let's also create the ready variable over here. We're also going to put a branch before setting the IK positions to check whether it's ready or not. So no change will be made to IKs until the legs are planted and being ready. We also need to assign it in the ABP. I think the problem is that the for each node does not give you a reference to the array elements. Let's get the array element using its index from the for each loop. Okay, now replace the struct pin. Okay. I also made another mistake. I named the toe bones completely incorrect. Let's fix that. Okay, I think we finally grounded all the legs. Okay, so now it's time to move the legs. Let's iterate over the legs first. Then we calculate the location which it's supposed to be. Then we update the leg at current index. And also, don't forget to check that the leg is not already planted. But you know, it should not be sliding on the ground, right? So instead of applying the hit location to the leg, let's calculate the Z offset individually. In order to do that, let's create a function to calculate the Z offset. Let's define distance and max step length as input and return the Z offset as output. Then all we have to do is to normalize the input and add a clamp node to limit the domain of the input. Then using Desmos, we can come up with a nice smooth curve which the leg can take when in the air. Okay, so now let's implement this. Now all we have to do is to add it to the Z value, but we also need to calculate the distance which character had taken from its previous location. But we don't know the previous location yet, but for now let's define the maximum step which our character can take. Let's define a new variable called prev location and let's initialize it to actor's location in the beginning. Now we can calculate distance which our character has traveled since last state. Okay, the problem is the range of Z function is from 0 to 1, so let's multiply it by some value called step height, for example. I think it started working. Okay, Now, the last step is to swap the legs when they reach their destination. First, we check if the distance to prep location is greater than the maximum step. Okay. Then, if it is greater than the max step, then we iterate over all the legs and negate their planted state. We also need to ground those legs that are not planted yet. In order to do that, let's raycast then. We also need to reset the previous location to current actor's location. It would be nice if we make a fallback trace if the legs did not hit the ground. So we make another ray trace from the trace end to, the robot's center. In that case, we can grab the edges. We can plant the legs on edges and on cliffs or whatever. Okay, but to fix the inconsistency, let's do this. If no trace hit the ground, we also need to negate the planted, right? Okay, congrats, we finally made it. Now let's add movement to our character. Okay, so in order to add movement to the character, we first need to make our character receive input from the player. In order to do that, we are going to use Unreal's enhanced input subsystem. To do that, we first need to get the controller and cast it to player controller. Then we can get the enhanced input. Then we can add a mapping context. But don't worry about the details here. The project is completely available to explore, and I will share you the links at the end. Okay, so now that the input is configured, let's add a camera and a boom to our character. Let's add a spring arm and a camera attached to the spring arm. Let's configure its position and giving it a bit of space. And done. Now let's auto-possess the character. Back to Blueprint, let's add some options. Enable orient rotation to movement. Now we can drag and drop a look action and write camera movement logic. Also, in spring arm properties, make sure to check use pound control rotation. Okay, it's working. Now let's write some logic for the movement. We can get the forward vector from actor's rotation. And then we can multiply it by y-axis of the input. I think it should be the control rotation instead of actor's rotation. My mistake. And we can do the same for the sideway movement. I almost forgot that we only need the yaw parameter of the rotator. That's weird. The problem is we did not rotate the offsets, so let's do that. So when calculating the legs location, we need to also rotate those offsets before adding it with the actor's location. Okay, looks promising, but ain't that bad? We can make it a little bit better by interpolating the IK positions. Truth is, further optimization of this quadruped is out of context of this video, and I will leave that to you. Besides that, you can also investigate this project on your own. I made it available in my GitHub account. And if you think this character looks more interesting to you, you can have this one too. I also made some comments on its blueprint for better readability. And you think this one is different, then it's not. The method I used to create it is the same, but I put more effort to make it look good. I hope you have learned something new afterward. And if it were too basic, my apologies. Please don't forget to share your opinions in this comment section. Anyway, thanks for watching, and you think this is good channel, go ahead and subscribe for more contents to come.